Good morning, good afternoon, and good evening to everyone who joins us from around the world.
We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be back, and we are looking at a really fascinating and, I have to say, a very dense stack of research today.
Today, we are exploring chemical bottlenecks and the autonomous future of discovery. And I have to admit, when I first started going through these papers, I had a moment. I think most of us, we live in this digital bubble. We think innovation is just exploding because our phones get a little bit faster every year, and the AI models, well, they seem to get smarter by the week.
That's absolutely the common perception. We equate progress with software, with code, and app updates, and it feels like the future just arrived on your device.
Exactly. But this research, it paints a very, very different picture. It suggests that while the digital world is sprinting, the physical world, the world of atoms, of molecules, the actual stuff that our phones and our cars and even our bodies are made of is, well, it's kind of hitting a wall.
A chemical wall, to be precise. And it's a fascinating contradiction, isn't it? We have the digital brain power to imagine these incredible technologies, hypersonic travel, limitless clean energy, medicines tailored to your specific DNA.
Right.
But we are increasingly finding that we just lack the physical materials to actually build them. We're being limited by chemistry.
Which feels so counterintuitive. You'd think after a couple of centuries of modern chemistry, we'd have the periodic table pretty much figured out.
You would think so.
But the core theme of our whole discussion today is about how we break through those limits. We're going to start by looking at how we do things now, this sort of human trial and error approach.
The Edisonian approach, as some of the papers call it.
Right. And then we're going to explore this shift to something that, honestly, it sounds like pure science fiction. Self-driving laboratories.
It absolutely sounds like sci-fi, but as the sources show, it is very quickly becoming science fact. We're talking about combining AI and robotics in a way that can do, and this is a quote, 100 years of chemical research in a single afternoon.
100 years in an afternoon. That's the hook. That's the thing. You just have to understand how it's even physically possible. Okay, before we get to the robots and the high-speed discovery, we really need to unpack the problem itself. We have to start with the foundations. What do we think we know about this material world problem?
So the foundational premise we have to establish is that global industrial innovation is dictated by chemical properties, not just digital logic. It's the silent governor of progress.
We just don't see it. We swipe on a smartphone screen and we don't think about the indium tin oxide that makes it conductive or the lithium cobalt chemistry inside the battery.
Exactly. But those are the hard limits. Those are the real world constraints. And the sources call these chemical bottlenecks.
Okay, so let's define that. What is a chemical bottleneck?
A chemical bottleneck is essentially a physical constraint in a material that limits the efficiency of a system or increases its cost, or both. It's the point where the laws of physics and the properties of atoms just say no to our engineering ambition.
And they're everywhere, right?
They are everywhere. A really great, tangible example from the research is energy transport.
Pipelines.
Pipelines, yeah. We think of them as just big, simple metal tubes. You pump crude oil in one end, it comes out the other. It seems straightforward.
But it's not like pumping water.
Not at all, especially with heavy crude oil. It isn't like water, it's incredibly viscous. The best analogy is trying to pump cold honey or even molasses through a very, very long straw.
So it's thick, it's sticky, there's a lot of friction.
A tremendous amount of friction against the pipe walls. And friction generates heat, which is just wasted energy.
Yeah.
Energy needed to move that heavy crude is massive just to overcome what's called viscous drag. That's a classic chemical bottleneck.
The crude oil literally wants to stick to the inside of the pipe.
Precisely. And the research highlights that a huge area of innovation is in new surface chemistries for the inside of those proclines coatings that are what we call oleophobic. They repel oil, letting it slide through with far less friction.
So right now, we are burning enormous amounts of energy just to move energy around the planet because the chemistry of the pipe and the oil are fundamentally at odds.
That's a perfect way to put it. It's an efficiency tax that we pay every single day because of our material limitations.
And it's not just pipelines. The one that probably affects everyone listening is in our electronics. The heat limit.
Oh, this is maybe the most urgent one. Silicon chips, the foundation of the entire digital revolution for what, 50 years now?
Oh, like,
They're hitting a hard physical limit. And it's not just about Moore's law and making transistors smaller anymore.
it's a temperature problem.
It's a temperature problem. Silicon just gets too hot. As we try to push more and more power through these chips for electric vehicles, for 5G base stations, for AI data centers, silicon can't handle the combined heat and voltage. It starts to degrade. The electrons don't behave properly.
It's like trying to redline an engine all day.
Yeah.
Eventually, it's just going to melt.
That's a great analogy. The engine overheats and seizes, so the entire industry is in a desperate search for what are called wide bandgap materials.
I saw that term. Silicon carbide, gallium nitride.
Exactly. These are materials that can operate at much higher temperatures and handle much higher voltages without breaking down. But manufacturing them, growing these perfect, flawless crystals, it's incredibly difficult and expensive chemistry. Any tiny defect in the crystal can ruin the whole chip.
So we have the design for the faster car, but we can't forge the engine block to handle the power.
Precisely. And then there's medicine. You mentioned the note about left-handed and right-handed molecules. This took me back to high school chemistry, and I have to say I never fully grasped why it was so important. It is immensely important. It's a concept called chirality. Many of the complex molecules in our bodies and in the drugs we make come in two forms that are mirror images of each other.
Like our hands.
The hand analogy is perfect. Your left hand and your right hand are made of the same stuff. They have the same parts, but you cannot superimpose them. A left-handed glove will not fit on a right hand.
Okay, so molecules can be handed. What's the practical implication of that?
In biology, shape is everything. A drug molecule works like a key fitting into a lock on a protein or a cell. One hand of a molecule might be the perfect key, a life-saving drug.
Yeah, on the other hand.
Its mirror image might be a key that doesn't fit the lock at all, making it completely inactive. Or worse, it might fit into the wrong lock somewhere else in the body and be actively toxic.
Toxic. You mean it can cause harm?
Absolutely. The most famous tragic example was the drug thalidomide in the 50s and 60s. One hand was a safe sedative for morning sickness. Its mirror image caused catastrophic birth defects. The drug was sold as a mix of both.
Wow. Okay.
The source material mentions a more modern example, coenzyme Q10 or CoQ10.
Right, the supplement you see everywhere for heart health, and it's in expensive anti-aging creams.
And it's vital for cellular energy. But when we try to synthesize a complex molecule like CoQ10 in a lab, it's incredibly difficult to control that stereoselectivity to get only the right-handed version that our body uses.
So you end up making both.
Often, yes. You run the reaction and you get a 50-50 mix, which means half of your product is the wrong shape. It's either useless or has to be painstakingly separated and thrown away.
That's a 50% waste rate built into the process from the very beginning. It's no wonder some of these drugs are so astronomically expensive.
It's a huge driver of cost and inefficiency. So you have these fundamental physical limits in energy, in electronics, in medicine. And the way we've traditionally tried to solve these problems by finding new materials is, according to this research, sort of broken.
And that gets us back to that Edisonian approach you mentioned.
Yeah, broken might be too strong a word, but outdated or painfully slow certainly applies. We call it the Edisonian approach after Thomas Edison's search for a light bulb filament.
He just tried thousands of different things until one happened to work.
Exactly. Bamboo fibers, platinum wire, cotton thread. I think the legend says he even tried a hair from a friend's beard. It's pure brute force trial and error.
You mix chemical A with chemical B, you heat it up, you cool it down, and you just hope something useful happens.
And if it doesn't, you clean out the beaker and you try mixing A with C. It's painstaking. It's slow. It relies on intuition, deep knowledge, and a huge amount of serendipity.
Yeah.
Just getting lucky. It's like looking for a needle in a haystack by picking up every single piece of hay one by one.
And hope is not a sustainable strategy, is it? Especially when we're facing what the sources call a crisis of scarcity.
This is the other half of the problem. We're not just slow at finding new things. We're running out of the easy things that nature has already provided. The research here on the critical mineral crisis is, well, it's sobering.
It really is. The section on the hydrogen economy stood out to me. We hear about this all the time. The dream of using electricity to split water into hydrogen and oxygen. Clean fuel, with the only emission being water vapor.
It's a beautiful vision of a clean energy future, but there is a very, very big catch.
And the catch is an element called iridium.
The catch is iridium. To split water efficiently using the best current technology, which is called PEM electrolysis, you need a catalyst. And the best catalyst we have, by far, is iridium.
And iridium is rare.
Iridium is one of the rarest stable elements on Earth. It's a platinum group metal. Most of it came to Earth via asteroids. It's incredibly dense, incredibly hard to work with, and incredibly expensive.
How rare are we talking about here?
The research suggests there literally is not enough iridium in all the known mineable reserves on the planet to scale up the hydrogen economy to the global level we would need to replace fossil fuel.
Wait, let me get this straight. It's not that it's too expensive. It's that it physically does not exist in sufficient quantities.
That's the terrifying reality of it. Even if we could afford to mine every last ounce, we couldn't build enough electrolyzers. It is a hard physical stop sign on the road to the hydrogen economy as we currently envision it.
That's a stunning bottleneck. It means the entire technology is fundamentally unscalable with current materials.
It is, and it's a similar story with batteries. We talk about lithium, but the real constraints are often cobalt and nickel. The supply chain is incredibly fragile. You have major ethical issues with cobalt mining, particularly in the Democratic Republic of Congo.
And huge environmental issues with lithium extraction, right?
Yeah.
The amount of water it uses in desert environments.
Massive water consumption, yes. And then you have to overlay all of this with the geopolitical angle. The data presented on mineral refining dominance is just staggering.
It's a strategic choke point.
It's the ultimate strategic bottleneck. One of the sources states that China currently dominates the refining of 19 out of 20 designated strategic minerals. We're talking market shares of 70, 80, sometimes over 90%.
And the research mentioned their recent export controls on gallium and germanium.
Right. Those aren't just obscure elements. They are absolutely critical for next-generation semiconductors, for high-efficiency solar panels, for fiber optics, for LEDs.
And also on something called heavy rare earths, like dysprosium and terbium.
They sound like they're from another planet, don't they?
They really do. What are they used for?
They are vital additives for the high-performance permanent magnets you need in wind turbine generators and the motors of electric vehicles. You add a tiny bit of dysprosium to a neodymium magnet, and it allows that magnet to operate at high temperatures without losing its magnetic force.
So without it, your EV motor overheats and becomes much less efficient.
Or it just fails completely. So when those export controls are put in place, it sends a shock wave through the entire Western technology sector.
So to summarize the foundation here, we're hitting physical limits with our existing materials. The new materials we need are often made of elements that are incredibly scarce, and the supply and processing of those scarce elements are controlled by a geopolitical rival. It feels like we're backed into a corner.
We are. It means we need a totally new way of doing science. We can't just keep digging for rarer and rarer rocks and hoping we find the right one.
We have to move from finding materials to designing them.
That's the goal. The entire field is trying to shift from commodity chemicals to specialty high-performance solutions designed on demand. If we can't get iridium, the mission becomes design a new material that acts just like iridium, but is made from abundant, cheap elements like iron, carbon, and nickel.
Which seems impossible.
Oh.
But that segues perfectly into our next section, frontiers. This is where we look at what might change everything, and it starts with a robochemist.
The rise of the autonomous laboratory.
Now, when I first read robochemist, I was picturing a humanoid robot in a lab coat carefully pouring liquids from one beaker to another.
That's the movie version, yeah.
But it's much more integrated and, frankly, much more powerful than that, isn't it?
Oh, absolutely. The definition from the research is a fully automated, integrated platform that combines artificial intelligence, robotics, and cloud computing. The key concept to get our heads around is that it closes the loop.
Okay, what loop?
The predict, make, measure loop. This is the fundamental cycle of all scientific discovery.
Predict, make, measure. Break that down for us.
Okay, so traditionally, a human scientist starts with a hypothesis. They predict. I think if I mix these chemicals in this ratio and heat them to this temperature, I will get a better catalyst. That's the predict phase.
Right, the idea.
Then they go to the lab bench. They physically weigh out the powers, dissolve them, mix them, put them in an oven. That's the make phase. It can take hours.
Okay.
Then they take the resulting material and put it in a machine to test its properties. That's the measure phase. Then they take that data, go back to their office, think about it, and decide what to try next. The whole loop can take a day, a week, even a month.
There's so much human latency in that cycle. We have to sleep, we get distracted, we have weekends.
An autonomous lab closes that loop electronically. The AI predicts a formula. It sends the instructions to the robot, which makes the material. The material is automatically moved to a sensor, which measures the result. And that data feeds back instantly to the AI, which uses it to inform its very next prediction. The loop goes from days to minutes.
It never sleeps, it never gets bored, it never needs a coffee break.
It just runs, 204/7. And the Northwestern University breakthrough with the megalibrary is just a stunning illustration of what the speed can accomplish.
This is the story about finding that iridium replacement we just talked about.
This is it. This is the payoff. So the researchers at Northwestern needed an alternative to that rare, expensive iridium for hydrogen production. Using the old Edisonian method, they might test one new combination of metals per day.
It would take centuries to test all the possibilities.
Exactly. Instead, they used a megalibrary approach. They took a small chip, and using a technique that's sort of like an advanced inkjet printer, they deposited millions of microscopic dots on that one chip.
And each dot is a different experiment.
Each dot is a unique chemical composition, a slightly different ratio of 4 abundant cheap metals: cobalt, iron, nickel, molybdenum. So instead of one experiment in a big beaker, they're running millions of parallel experiments on a surface the size of a postage stamp.
That's just a mind-boggling level of parallelization.
It is. They then scanned this megalibrary with a probe to measure which dots were best at catalyzing the water-splitting reaction. And the result?
In one afternoon.
In a single afternoon, they screened more combinations that have likely been tested in that field in the last century. And they found a new material, a new catalyst, that performs just as well as iridium but costs thousands of times less.
100 years of research in an afternoon. That claim is starting to sound plausible.
It's not just plausible, they did it. And it proves this revolutionary idea. We aren't limited by what's in the ground. We're limited by how fast we can test the infinite combinations of what's already abundant. It democratizes discovery. You don't need a lucky iridium mine in South Africa. You need a fast robot in Illinois.
But it's not always about just replacing the human entirely, is it? The research from the University of Chicago and Argonne National Lab points to a different model, the AI advisor.
Right. This is a more collaborative approach. It's less about a lights-out lab and more about augmenting the human scientist's intuition. They actually took their inspiration from, of all places, Wall Street.
Stock trading algorithms.
Exactly. In high-frequency trading, you have algorithms that can process millions of data points a second to spot trends that are invisible to a human trader. But for the big strategic decisions, you often still have a human portfolio manager who makes the final call.
Okay, I see the parallel.
The AI advisor does the same thing for chemistry. It sifts through all the experimental data, it reads the scientific literature, and it suggests to the human researcher, based on everything we know, the data suggests your next experiment should be this specific combination.
So the AI is the tireless analyst, and the human is the CEO who makes the strategic decision.
It's the Centaur model, half human, half machine. The AI handles the brutal data crunching, and the human handles the intuition, the context, and most importantly, the safety checks.
And did it work?
It improved the performance of a polymer they were developing by 150%. And here's the fascinating part. The AI identified key factors that the human researchers had been ignoring, subtle variations in stirring speed or humidity that they had dismissed as noise.
So the AI saw a pattern in what the humans just saw as random statistical noise.
That's exactly it. We have our biases. We think, oh, that little fluctuation couldn't possibly matter. The AI has no biases. It just looks at the data and says, actually, the data shows that fluctuation correlates strongly with your best results.
Wow. But then you have the other end of the spectrum, the fully autonomous systems, the true self-driving lab.
This is the lights-out lab you were talking about. And yes, the name implies you can literally turn the lights off and go home because the robots don't need them.
And the A-Lab from DeepMind in Berkeley is a prime example.
A-Lab is incredible. The paper reports it independently discovered and synthesized 41 new materials in just 17 days. And the key technology it uses is something called active learning.
Active learning, what does that mean in this context?
It means the system learns as it goes, in real time. It looks at the result of experiment A to decide on its own what to do for experiment B. It's not just running a pre-programmed list of recipes.
So if a reaction fails,
Yeah.
What happens?
A simple robot would just report the failure. An active learning system says, okay, that failed. The powder didn't crystallize properly. The data suggests that might be because the oven was 5 degrees too cool. For the next run, I will increase the temperature by 5 degrees and try again. It's troubleshooting itself without any human intervention.
That's a huge leap. It's the difference between a machine that follows instructions and a machine that actually thinks.
And then there's the example from China, which adds another layer of complexity: a mobile robot.
The AI chemist. This one actually moves around the lab.
Yes, it's a robotic arm on a mobile base. It can move between different instruments, the furnace, the spectrometer, the chemical stores, just like a human researcher would walk around a lab.
And they gave it this wild task involving Martian meteorites.
This is where it gets really futuristic.
Yeah.
The goal was to simulate what we'd have to do on a mission to Mars. We can't ship all the oxygen and fuel we need. It's too heavy and expensive. We have to make it there from the resources on the ground.
In situ resource utilization, ISRU.
Exactly. So they gave this robot samples of Martian meteorites and a single goal: figure out the best catalyst to produce oxygen from the materials in these rocks.
And it did this on its own.
Completely. It first ran over 3 million theoretical calculations in its AI brain to predict the best chemical combinations. Then it physically went to its chemical station, mixed the most promising candidates from those simulations, heated them, and tested their performance. All without a single human command. It simulated the autonomy you'd need for a Mars base millions of miles from Earth.
It's incredible. It's basically an autonomous field scientist for another planet.
It is.
Okay.
Now, of course, the brains behind this whole operation are just as important as the robotic hands. We have to talk about digital chemistry and the role of large language models.
LLMs. Most people think of them as chatbots, like ChatGPT.
Mhm.
But they're being used for actual science.
In a very powerful way. The research highlights systems like ChemCrow and Co-Scientists. These aren't just chatbots, they are AI agents. They can do more than just talk about chemistry.
What can they do?
They can browse the internet to find a published recipe for a chemical synthesis. But the part that blew my mind was that they can then find and read the instruction manual for the specific robotic equipment in the lab.
That's something most humans refuse to do.
I was going to say that puts them ahead of about 90% of us right there. The AI reads the technical documentation for a liquid handler or a robotic arm, and then it writes the Python code necessary to control that arm and execute the steps of the recipe it just found online.
That is a staggering capability. It's bridging the gap between abstract knowledge, the what, and the practical execution, the how.
And to do this, they need to be trained on colossal amounts of data. The source mentions a project called Open Molecules 2025, or OMOL 25.
This is a data set from Meta and Berkeley Lab, right?
Yes, a massive open source data set with 100 million molecular snapshots. These are the results of quantum mechanical simulations. It's an enormous library that trains an AI to predict chemical properties and reactions 10,000 times faster than running those traditional physics simulations from scratch.
10,000 times faster. These numbers are just hard to comprehend.
It's what enables the concept of digital twins.
A virtual replica of the experiment.
Exactly. Before you waste a single drop of a rare or expensive chemical, you run the experiment 1,000 times in the computer. You let the AI find the optimal conditions in the simulation. It's like a flight simulator for chemistry. You can crash and burn 1,000,000 times virtually so that when you do the one real experiment, it has the highest possible chance of success.
So we have the robot bodies, we have the AI brains. What are they actually creating? We talked about the iridium replacement. But the research also mentions these new supernatural materials.
Yeah, supernatural is a great evocative term for it. It refers to materials that are artificially engineered to have properties that you just don't find in nature. Metamaterials are a perfect example.
How do they work?
It's not about the chemical composition so much as the physical structure. By engineering patterns into a material at a scale smaller than a wavelength of light or sound or whatever you're trying to control, you can make it behave in impossible ways, like creating invisibility cloaks.
Okay, invisibility cloaks. Are we talking Harry Potter here?
For a specific wavelength of light like microwave radiation, yes. The metamaterial structure bends the waves around the object as if it weren't there. But the more practical applications are just as amazing. The research talks about using metamaterials in the foundation of a building to redirect seismic waves from an earthquake.
So the earthquake literally flows around the building instead of shaking it apart.
That's the idea. The building becomes, in a sense, invisible to the earthquake. Or, for telecommunications, you can create smart surfaces that bend 5G or 6G signals around obstacles like walls or trees, solving one of the biggest problems with those high-frequency signals.
The building itself becomes part of the antenna network.
Exactly. And then you have diamond semiconductors.
I always think of diamonds as being for jewelry or for cutting tools.
Well, in the world of electronics, diamond is considered the potential ultimate semiconductor. It has the highest thermal conductivity of any known material. It just whisks heat away instantly. It can also handle ridiculously high voltages.
So if our chips were made of diamond instead of silicon, they could run faster and cooler.
Much faster and much cooler. Your EV could charge in minutes without the power electronics overheating. The challenge, again, is manufacturing growing large, perfect, single-crystal diamond wafers is one of the hardest materials science problems there is.
And batteries, of course. Solid-state batteries.
This is a huge one. The goal is to replace the flammable liquid electrolyte inside our current lithium-ion batteries with a solid material. This would make them much safer, no more fires, and allow them to store more energy in the same space.
But there's a problem, right? The interfacial resistance problem.
That's the bottleneck. Imagine you're trying to build a bridge out of two giant flat rocks. No matter how perfectly you polish them and press them together, there will still be microscopic gaps between them, air gaps.
And ions can't jump across those gaps.
Exactly. The flow of energy just stops at that interface.
Yeah.
So these autonomous labs are working overtime to design new solid materials that can form a perfect, seamless bond at the atomic level, solving that resistance problem.
And what about sodium-ion batteries?
A very promising, cheaper alternative to lithium. We have a virtually infinite supply of sodium. It's in every ocean. Sodium-ion batteries aren't quite as energy-dense as lithium-ion yet, so you might not see them in a high-end smartphone or a performance EV right away.
But for other applications.
For stationary grid storage, for storing solar energy from a solar farm to use at night, they could be a game changer. They're made from cheap, abundant, and geopolitically stable materials.
This all sounds incredible. It sounds like a technological utopia is just around the corner. But I have a feeling it's not quite that simple. This is where we need to get into the active debate. Where is the science still unsettled? What are the big hurdles?
You're right, it's far from a solved problem. And the first major debate is happening right there in the lab itself. The human-in-the-loop model versus the fully lights-out lab.
Basically, do we trust the robot to run the show completely on its own?
That is the fundamental question. The fully autonomous lights-out model is incredibly efficient, but there's a massive trust issue. We know from consumer-facing chatbots that AI can hallucinate. It can just make things up.
Right, we've all seen examples of it inventing historical events or citing court cases that don't exist.
Now imagine that in a chemical lab. A hallucination isn't just a factual error. It could be a recipe for a highly toxic substance or an explosive mixture. If the AI is only optimizing for, say, reaction speed, it might not have the common sense to know that a particular combination produces cyanide gas as a byproduct.
So unless safety constraints are perfectly programmed into its training data, it's a potential danger.
A huge potential danger. And then there's the related black box problem. Let's say an AI designs a revolutionary new room temperature superconductor. But the reasoning for why that specific combination of elements works is buried deep within the trillions of parameters of its neural network. We can't understand it.
It's the difference between having a recipe book and actually understanding the principles of cooking.
A perfect analogy. And for scientists and for regulators, the why is everything. If we don't understand the fundamental principles of why a material works, can we really trust it in a passenger jet or a medical implant? What happens when it encounters conditions the AI never tested for? We need what's called explainable AI or XAI, and we're not quite there yet.
And this all relies on the data the AI is trained on. The issue of data quality and standardization seems like a huge, unglamorous, but critical hurdle.
It might be the biggest hurdle of all. An AI is only as good as the food it eats, garbage in, garbage out. And unfortunately, a century's worth of chemical data is a mess.
It's handwritten in notebooks from the 1970s.
It is. It's in non-standardized formats in thousands of different journals. One lab reports their experimental yield one way, another lab reports it a completely different way. There's no single, clean, structured format.
And there's a bias in what gets published, right?
A massive publication bias. Scientists publish their successes. If an experiment fails, if a reaction produces nothing but useless brown goo, it rarely gets written up and published. It just stays in the lab notebook.
So the AI is training on a data set that's full of all the wins but it sees almost none of the failures.
Which gives it a completely skewed view of reality. It might think certain reactions are easy and reliable because it's only ever read the 5 papers where it worked, not the 500 unpublished attempts where it failed. The sources say there is a desperate, urgent need for clean, standardized public databases, a chemical science database that includes both positive and negative results.
What about the physical robots themselves, the hardware? You mentioned the challenge of powders.
Yeah, the hardware constraints are a real thing. Automating liquids is a more or less solved problem. Pharmaceutical companies have used liquid handling robots for decades. Pipetting a clear liquid is easy for a robot.
But chemistry isn't always liquids.
It's often not. It's solids, it's fine powders, it's thick, viscous slurries, it's high temperatures and high pressures. And powders are a roboticist's nightmare.
Why is that?
They clump. They stick to surfaces due to static electricity. They can clog the tiny tubes that the robot uses. Trying to get a robot to accurately scoop and weigh out 10 milligrams of a fluffy white powder, transfer it to a vial without spilling a single grain, and do that reliably 1,000,000 times. It is a colossal engineering challenge.
It sounds so mundane, but a jammed powder dispenser can shut down your entire multi-million-dollar autonomous laboratory.
It's the mundane things that often stop progress in its tracks. And that brings us to maybe the biggest hurdle of all, which has its own name, the Valley of Death.
Manufacturing scalability.
This is the classic chasm in material science. It is one thing for the A lab at Berkeley to make a few milligrams of a new supernatural material on a lab bench. It is a completely different universe of problems to figure out how to manufacture 100 tons of that material affordably and reliably for an industrial customer.
The biopharma case study in the research was really illuminating here.
It's a perfect example. Gene therapies often use modified viruses, viral vectors, to deliver the genetic payload into a patient's cells. They are incredibly effective, but notoriously difficult and expensive to manufacture at scale.
They're biological, they're finicky.
Exactly. So the industry is trying to shift to non-viral delivery methods, which are simpler synthetic chemicals. But as they try to scale up manufacturing, they start using more and more single-use plastics, big disposable bags, and tubing to ensure sterility.
And this creates a new problem, leachables.
A brand new bottleneck. Trace chemicals from the plastic manufacturing process can leach out of the bags and into the final drug product. You solve the biological manufacturing problem, but create a new chemical contamination problem. It's a constant whack-a-mole.
And for more traditional chemicals, there's this ongoing debate between batch processing and continuous flow.
Right. Batch processing is the old school way, like baking a cake. You put all your ingredients in a giant reactor, mix them, let them react, and then you take the product out and clean the reactor for the next batch. It's flexible, but it can be slow and inefficient.
Continuous flow.
That's the modern approach, more like an assembly line. Your reactants are continuously pumped through a series of tubes and reactors, and the finished product continuously flows out the other end. It's highly efficient and consistent, but it's very expensive to set up, and it's not very flexible. If you want to make a different product, you might need a whole new assembly line. The industry is really wrestling with which approach is better for these new AI-designed materials.
Okay, so we have the potential for AI hallucinations, messy data, clumsy robots, and this huge valley of death between the lab and the factory. But let's assume, for the sake of argument, that we figure these things out. What does that world actually look like? This brings us to the implications.
And the implications for the green transition and creating a truly circular economy are profound. Let's start with recycling.
Which right now is pretty broken for a lot of materials, especially plastics.
It is. A lot of what you put in your recycling bin doesn't actually get recycled, particularly thermoset plastics, the hard, rigid stuff used in car parts or wind turbine blades. They're held together by strong, cross-linked chemical bonds. You can't just melt them down and remold them like a plastic bottle. They just burn.
But with these new technologies,
With AI-designed catalysts and enzymes, we are on the verge of true chemical recycling. We can design molecules that can go in and selectively snip those tough chemical bonds.
like molecular scissors.
Exactly. Unzipping the plastic polymer back into its original building blocks, its monomers, which can then be used to make brand new virgin quality plastic. It turns a landfill problem back into a valuable raw material.
And the research also talks about e-waste.
The urban mine. There is literally more gold in a ton of discarded smartphones than in a ton of ore from many gold mines. Same for rare earth elements. The challenge is getting them out safely and economically.
And this is where hydrogen decrepitation comes in.
It's such a cool technique. You take a chunk of an old EV motor or a hard drive magnet, you expose it to hydrogen gas under pressure. The hydrogen atoms work their way into the crystal structure of the metal alloy, and then they cause it to rapidly expand and shatter from the inside out.
It just crumbles into powder.
It turns the solid magnet into a fine powder, making it incredibly easy to chemically separate and recover the valuable rare earths like dysprosium and terbium. It's far cleaner and more efficient than just melting the whole thing down in a furnace.
That's a huge deal for closing the loop on that critical mineral crisis we started with.
It's absolutely essential. And then there's direct air capture, or DAC, for pulling CO2 out of the atmosphere. The bottleneck there is finding the right material, a chemical sponge that can effectively grab CO2 molecules, which are very dilute in the air, but then release them easily without requiring a ton of energy.
A sponge that can be easily squeezed.
That's the perfect analogy. And the AI labs are churning through millions of potential molecular structures to find the perfect one. And in a really neat self-referential twist, one innovation mentioned is using new glass fiber membranes for evaporative cooling of AI data centers.
Wait, run that by me again.
The AI systems that are designing these new materials consume enormous amounts of energy and generate a lot of heat. This new membrane technology can cool those data centers much more efficiently, using less water and energy.
So it's a virtuous cycle. The AI is designing the very materials that will allow it to run more sustainably.
That's the dream, anyway. And beyond the environmental implications, you have massive economic and geopolitical shifts.
We talked about China's dominance in rare earth refining. This seems like a direct counter to that.
It is. If a country can use its own autonomous labs to design a high-performance battery that uses sodium instead of lithium or iron instead of cobalt, the geopolitical map of energy is completely redrawn.
You're no longer dependent on a mine on the other side of the world.
You achieve energy sovereignty. Your national security becomes dependent on your scientific and technological capabilities, not just your access to mineral resources. It fundamentally changes the balance of power.
And it creates what the research calls a supernatural market.
Yes. If we can reliably design and manufacture molecules that are more potent, more durable, or more effective than anything found in nature, it changes the entire pharmaceutical and materials industry. We move from just finding remedies in plants and fungi to engineering perfect molecular solutions from the ground up.
And of course, this completely transforms the workforce. The chemist of the future is not what I pictured in high school.
Not at all. The chemist of the future isn't just someone skilled at mixing beakers. They are a data scientist. They are coding in Python to control a fleet of robots. They are an AI supervisor. The lab code is still there, but it's worn over a laptop.
Which brings us to our final provocation.
Well,
The big thorny question to leave everyone thinking about.
and it's a big one. We've established that we are moving from an era of discovery, of finding what nature has already made, to an era of creation, of building what we need from first principles. But this raises a profound legal and even philosophical question.
Okay.
If a fully autonomous AI, a lights-out lab, runs millions of experiments, analyzes the data, and on its own designs a new molecule that cures Alzheimer's, who owns that discovery?
Wow. Is it the programmer who wrote the AI's code? Is it the chemist who turned the machine on and gave the goal? Or does the AI itself hold the patent?
Or is it the company that owns the server farm? Or if the AI was trained on decades of publicly funded research data, does the discovery belong to the public? Our entire legal framework of intellectual property is built around the idea of a human inventor. It is completely unprepared for this question.
That is a lot to think about. From the physical constraints of a pipeline, to a robot chemist on Mars, to the legal personhood of a discovery algorithm.
It is a brave new world being built, one atom and one bit at a time.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.